Active Physical Science, Chapter 1, Section 2, Physics Talk, Errors in Measurement, Random Errors. There is no exact measurement. In the Investigate, when you used your stride length as the measuring tool, the distance of the hallway was different for many of the groups. If you tried to improve the measurement by using a meter stick, you found that there were still differences in the measurement. Even if you had used a tape measure, there would still have been differences in your measurements. Physicists know that all measuring tools produce random errors or errors that cannot be corrected by calculating. It is the responsibility of the student scientist to record all the values of a measurement and recognize that the data will include random errors. Every time you measure the length of your desk, you might find that the measurement is different from a previous value by 1/10 of a centimeter or 0.1 centimeters. This difference could be in either direction. You can use a more precise ruler, and that may decrease this random error or uncertainty to only 0.05 or 5/100ths of a centimeter, meaning plus or minus 5/100ths of a centimeter. However, the uncertainty can never be completely eliminated. Both the measuring tool and the person doing the measuring are responsible for the uncertainty. A meter stick that has only the centimeters noted would have a greater uncertainty than a meter stick that has the millimeters noted. A meter stick that has millimeters noted may still have a large uncertainty if the person using it is not very careful in aligning the meter stick with the length being measured. In your measurement of the distance, you found different distributions of measurement. If you made histograms, as shown below, of the length of a hallway using your stride, this figure here, the meter stick, this middle figure, or a tape measure, the right figure, you can get a sense of the uncertainty in each type of measurement. The middle value is probably the best guess for the length of the room, but there will always be an uncertainty surrounding that value, as shown by the spread to the left and right of the middle value. Okay, so here's the length of the hallway, using strides, using a meter stick, using a tape measure. The middle value is probably the best guess, so here's your best guess on each one. And then there's an uncertainty which shows the spread to the left and right are the uncertainties. Best guess is your middle value. Okay. Systematic errors. There are also systematic errors. If you mistake a yardstick for a meter stick and report your measurement is 4 meters when it's in fact 4 yards, that is a systematic error. Every measurement you record with that yardstick will have this error. Systematic errors can be avoided or can be corrected by calculating. Accuracy and precision. Now we're talking about the arrows, so I'm going to move down a little bit so we can see. We're talking about this chart. Accuracy and precision. In shooting arrows at a target, you can have accuracy and precision by getting all the arrows in the bullseye, which is accuracy and precision. You can have precision but not accuracy by having all the arrows miss the bullseye by the same amount, which is this figure right here. Okay. You can also have accuracy but without precision by having all the arrows surrounding the bullseye spread out over the area. Right figure. Okay, so that's this one. Notice that here the average position is the bullseye's accuracy, but not one of the arrows actually hits the bullseye. They're talking about this one. Measurements can also vary with accuracy and or precision, just as the arrows in the target. People do not always need the same level of precision in their measurements. One decision you must make is how precise a measurement you want. For example, in motor racing, horse racing, or Olympic skiing, time has to be measured to the thousandths or tens of thousandths of a second. But when a painter estimates the time required to paint a customer's house, she or he may only need to know the time within a few hours. As you increase the need for precision, the measurement becomes more difficult and often more expensive to make. Okay, so here again we have accurate and precise, precise but not accurate, and accurate but not precise. All right, let's go down. The SI system. In active physical science, in active physical science, you will be using the International System of Units. The units are known as SI units, abbreviated from Le Système International de Units. This is the system of units that is used by scientists. The system is based on the metric system. All units are related by some multiple of 10. There are 7 base units that can be combined to measure all scientific properties. The base units that you will use in active physical science are shown in the table. Here's the table if you want to take a screenshot of it now, or you can also, it's also available in your PDFs on Google Classroom. But this table has 3 categories, quantity, unit, and symbol. And then within each row, you're able to connect those. So quantity, so for length, the unit is meter, and there's your symbol, M. For the quantity of mass, your mass is measured in kilograms or kg. Time is measured in seconds or S. Temperature is measured in Kelvin or K. Current is measured in amperes or A. You will also be using other units that are a combination of these base units. You will be introduced to these units when you need to use them. The best way to learn units is to use them frequently and correctly. It is not helpful to memorize lots of units. Okay, so they're saying that as you use them frequently, but also I don't want you to worry about memorizing them. You will eventually memorize them, but it's also important to have this chart handy so that you can, as things come along, you can just refer to this chart, and then you don't have to get stressed out about memorizing it all. You just refer to this chart. Okay. In this section, you measured the length of a distance in meters. The meter is the base unit of length. Other units that you will use for measuring and describing length are the kilometer, the centimeter, and the millimeter. These 3 units are made up of the base unit, meter, and a prefix. An important feature of the metric system is that there is a single set of prefixes that relates to larger and smaller units. All the prefixes are related by some power or multiple of 10. So here's another chart where you have your prefix. So that means you multiply by 1,000. And then there's some examples of it. All these examples are length. So that centi or C, that's having you multiply by 10 to the negative second power. Milli or M, you're multiplying by 10 to the negative third. Really just moving the decimal point 3 spaces to the right, 2 places to the left, 3 places to the left. So really just moving that decimal point. Oh, and there's your chart that tells you how to do that. Okay. Driving the roads and United States measurement. Let me go down a little bit. Driving the roads in United States units of measurement. The United States does not use the metric system for everyday measurements. Distances along the road are measured in feet, yards, or miles. Speed limits are posted in miles per hour rather than kilometers per hour, as they are in many other countries. Below are some conversion factors for length in the United States measurements. 12 inches equals 1 foot. 3 feet equals 1 yard. 5,280 feet is 1 mile. In this chapter, Driving the Roads, United States measurements will be used to express distances and speeds with respect to driving and traffic. In the classroom, you will use the SI units for measuring. When obeying speed limit signs, it is important to know what units of measurement are being used. Okay.